say that's the shape, the S shape is always S shape, or it could change? It could change, right?
It can change how it looks, but it's always going to be sigmoidal.
Okay.
It's always going to have that curve shape. And that's because, imagine the limits for any reaction. For any reaction, if I'm at 0 temperature, I don't get any reaction, so G is essentially, very small, right? And changing the temperature is not going to make a big impact until I get to an appreciable temperature at which reaction starts to occur. Then I get my large shift, which is I release a lot of heat. But then once I'm really, really hot, I've run out of reaction to do. So all I can do, the maximum of this, right, is when this part in the parentheses is equal to a conversion of 1. And then I'm done. I can't go beyond that. So it's always going to have that shape. Doesn't matter if it's first order, second order, 0 order. Doesn't matter. Reversible, irreversible. There. Okay, and like I said, we call this ignition and we call this extinction. So how do I access 6? What do I do in order to get to 6? Yeah, I can't, if I put it in at whatever this, if we labeled our inlet temperatures here, that would have been the 3rd on our plot. We made 5 lines, so that's 5 inlet temperatures. If I start at T3, I'm going to hit steady state 4. All right, well, there's nothing I can do about that. That's the steady state solution. The way to get to 6 is I have to keep heating, hit the ignition, and then come back. Because if I'm already hot, I can cool, and I'll stay along this curve until what temperature? The extinction temperature. But that's if I'm already hot. If I'm cold, and I'm just heating up, I'll stay along this curve until what? The ignition temperature. All right, so you guys know how to access steady state 6. Better. How to operate at that condition. How to start up. How do you start up the reactor in order to operate at the 6th point on that plot? Yeah.
Now, if you want to operate at 6 such that the temperature won't increase out of control, but in order to do that, you have to heat it up to 2.9, whatever the ignition temperature is. And don't you really have to have a system that can take the out of control temperature?
Yeah. This isn't always like the end of the world. Sometimes it can be if you have an undesired reaction that happens at those high temperatures and high conversions, or if there's a safety issue where you want to stay out of that high temperature, high conversion regime. A lot of times you want to operate at the high temperature, high conversion regime because you want to make stuff. So the higher conversion, you're happier. But there are times where you don't want to mess with this curve. There are times where you explicitly want to operate in that curve. The other thing that you can do, though, is you can feed your feed at a higher temperature than your reactor. Right? So that's the other way to access that temperature. But more commonly, you increase it, you hit the ignition point, and then you start to cool back down, and you're okay. But either way, I mean, it's the same thing. I mean, you increase your feed, you're just shooting over here, and then you come back. That's how you increase that's how you get to 6. You increase your feed temperature, and then you cool back down.
So if you had like a reaction that you couldn't tolerate it being at 9 or greater,
You mean at 8 or greater?
Sure.
Yeah, I mean that's the, yeah, 8 is the one directly above the ignition point.
Then like for any period of time,
Yeah.
you could never access.
No, you can't, right. You can't operate at 6 because it would require you to do something unhappy, You would violate one of your cardinal rules for that reactor, which is don't heat it above this point. Yeah.
Generally speaking, will those points along the top and bottom of the 3, 6, 8, 9, the temperature differences are relatively small, right? Or not always?
That's what can depend upon the reactor, the reaction itself. But no, I mean, these can be substantial temperature differences. These are not like 10 degrees. These are closer to a couple of hundred. But that depends a lot on the activation energy of the reaction and the cooling profile that you're using. Any other questions? Is that possible? This is more of a psychological question than anything else, right? Would he draw it on the board if it were impossible? I feel like that changed some answers. Yeah, that's possible. How many steady states do we have? We're jumping around a little bit. I'm trying to get caught up in the notes.
Is that from multiple reactions?
You know, you're just ruining it for me here. Yeah, there's 5 steady states. Which ones are stable, which ones are unstable? So let's call this A, B, C, D, E. Which ones are stable?
A and E for sure.
A and E for sure, all right. Any others?
C.
C. Just look at the slopes, that's it. You guys are experts. What can cause this?
Multiple reactions.
Multiple reactions, yeah. If you have something like A to B to C, so why? Yeah.
The C may the B to C reaction may operate at a better temperature than the A to B reaction.
Yeah, that's a good way of putting it. This first hump, you can think of this as like, okay, now A to B is basically done. I've done a lot of A to B. So you hit that magic sweet spot for the reaction A goes to B. And that causes you to have that dramatic increase in the heat generation term. And then later you hit the sweet spot for B goes to C. And so because you have 2 different reactions, they have 2 different sweet spots, and that gives you those 2 sigmoidal things which are now connected, and you get one big nasty thing. Yeah?
Will that always be like continuous and nice like that? Or?
Yeah, by definition they have to be, because you can't do B to C unless A to B has occurred. Right? Now this is for a series reaction. What if they were in parallel? What would it look like then? Could you have 2 humps like that for parallel reaction? Yeah, you still can. I find it easier to think about a series reaction, but a parallel reaction, and it's for the same reason, which is that each reaction has its own sort of sweet spot.
Yeah, but what if they're right next to each other?
Then it would just, you wouldn't notice it. You know, if I add 2 curves like this, and they have that same sort of critical temperature where they shoot up, it's just going to look like that. But if they're different, right, if the one for reaction 2 looks like that, then you're going to see both of those humps when you sum the 2 together. So the only difference between the parallel and the series reaction is that in the series case, I'm depending on A to B in order to do B to C. But in a parallel case, that's not true. Right? It's simply taking the sum of the 2 reaction energies times each of their extensive reaction. And that gives me the amount of heat generated. There's no interdependence between the 2 extensive reactions. They can just both occur. Of course, that's true unless I consume all of A by making a bunch of B, then C can't react anymore. So they're still limited by each other in the sense that both of them are consuming A. So when you're out of A, both reactions have to stop. But it's just a different relationship from the series one where B to C can't happen at all until A to B has occurred. All right, so that's what we're going to talk more about on Thursday, are multiple reactions in non-isothermal systems. But I wanted to bring it up here just to emphasize that now you guys know which steady state solutions are stable and which are unstable. So, stable or unstable?
If the slopes are the same, then I don't know that. Stable-ish.
Stable-ish. Those are the temperatures where you just need to be careful. You can survive a perturbation at those temperatures, but if the perturbation is too large, here it actually matters, the direction matters, right? If the perturbation's in this direction and it's too large, then I'm going to shoot up to the high temperature. That's what ignition means. If I'm at 100 and I accidentally go to 110, now I'm going to shoot up to the higher temperature. It is more stable in this direction though, because if I get colder for some reason, G is greater than R, so it just heats me back up. So they're pseudo-stable. They're stable in one direction, but not the other.
Is that the definition of stable?
Sure. You define the term. You'd have to tell me the definition. Don't make up words on tests. So the other thing that we had up on the board was we defined this little S function, which was equal to the slope of G versus T at the tangent point. And then we also had dr dt. And this is true at all temperatures. Oops. The inlet heat capacity times 1 plus kappa. And so we could plot the slope